So today we have friction factors for spheres on our menu. What are friction factors? Why are we using them? I'm hearing a whole lot of mumbling. Let's drink a sip of coffee and let's try again. So what are the friction factors? Or why do I need them?
Because we want to predict behavior in complex systems.
Complex systems, and what is describe complex? Why isn't Darcy's law or those equations? Why aren't they enough? So we want complex flow regimes as well as the systems, right? So far we mostly dealt with laminar flow, and friction factors basically enable us to go a little further and also look at the regimes that are not necessarily laminar. Now, in terms of details of the equations for turbulence, we are not going to go into those at all. Sorry. But we are going to use the friction factors nevertheless. So I'm at 30% power, so better save this. Sorry, thanks, Lauren, again. There we go. Can't have both of these in this one. They don't fit. All right. Okay, so let's get going. So today we have friction factor, or deriving friction factor for SpherePack. And unlike for our tube or for flow around the sphere, we had formulas to start with, right? So it was relatively easy to just start with whatever we had, analytical derivations that we have for laminar flow, and define something through that. The whole point of friction factor is like, okay, maybe even if you start from analytical derivation, what you want to end up with in terms of definition of this friction factor is measurable quantities. So it has to be defined in things that are measurable, because then we can go and do a whole lot of experiments and figure out and fit them and see whether the formulas are matching. So with SpherePacks, of course, there's no such thing as analytical formula. So there will be a whole lot of hand waving and stretching as we go through derivations. So essentially we will have our upscaling similarly how we derived Harman-Coseni. We will have that in mind as some sort of guiding logic, okay? But nevertheless, at the end, there might be parameters that we come up with, but they don't fit the experiments the best, then we will adjust the parameters simply to fit the experiments. So bear that in mind, because with upscaling, I don't have the exact formulas. Something has to be thrown away, so I do need to adjust. Don't be upset because of that. Okay? So let's get going. So what is our just two conceptual models that we've had, or that one can use in friction factors or derivation of anything in SpherePacks? One is I'm flowing around grains, so I could try to upscale, and that part we actually skipped this year, but one can actually figure out, oh, I have equations for flow around the single sphere. I can actually put those together in a way and upscale flow through multiple spheres or around multiple spheres at the same time. That's one way. And more prevailing way, because conceptually it's much more simple way, is that of imagining some sort of tortuous tubes across that SpherePack, right? And typically when we are upscaling, we are often just assuming tubes that are not intersecting, because intersections is not something I can deal with analytically or in any kind of upscaling. If I want to deal with intersections, then I go and simulate and do actual simulation that actually deals with that. So in any kind of upscaling, we're typically going to throw away intersections, and we're typically going to throw away inertial factors of any sort, So I might actually imagine that my tube is tortuous, okay? But when there's certain inertia because of that and slowdown in the flow. But when I'm applying formulas for that tube, I'm kind of straightening it out in my mind, okay? And putting down the equations as if it were a straight tube across the packing. So again, there are certain things we simply need to throw away, otherwise we are unable to upscale. You cannot take care of all of the details and still upscale. You have to kind of go with the gist of things. So the way we're actually going to go is we're going to kind of dance between this friction factor for some sort of SpherePack and or packing of spheres and these tortuous tubes through it, and just like having tubes or a bed. So the way it's going to go is the following. So just keep in mind, so I'm going to write that down, just keep in mind the two ways to think about flow through SpherePack. It's tortuous tubes, and I cannot write tortuous or spell tortuous on a Monday morning. It's tubes through the pack versus flow around single sphere kind of multiplied. And essentially, in any kind of upscaling, what always sticks is the models that are simpler to think about. Okay? So if you want to be famous and you want to derive something, then start simple. Okay, those are probably already gone though. So if you come up with a model and you come up with a very complex model, it's not going to take off. Okay? The more complex the model, A, it's harder to think about. B, it's more likely to have multiple fitting parameters, and it's going to be extremely difficult for researchers to have all of the parameters or to be able to fit them correctly. So even if a very sophisticated model exists, often it's not used simply because we're unable to fit all of the parameters, so we go with simpler one that we can. Okay? Which is why we continue to use Darcy's law even in cases where it's not strictly applicable. Right? Because yes, we know we need to maybe add second order parameters and what's in terms of velocity and what not. But we can't always accommodate that because we don't have enough data to fit. So bear in mind that the simpler, the better sometimes. Okay, so first we're going to define, I'm going to change my color here. Okay. I'm going to define what I call friction factor for a bed of spheres, F bed, similar to what we have for a tube, but I'm going to use the parameters that I have for sphere packing. And then I'm going to actually kind of try to twist and tweak this definition to make it something that is better fitting with my data. So I'm just going to do a definition as 1 over 4. So if I had a tube, I had definition of the fanning friction factor was diameter over tube defining by length, and then pressure difference, and then 1/2 rho, and then the average VZ square, right? That was my vision. Now, What I'm going to put here instead, because I have a sphere packing, I'm going to put V0, where V0 is my Darcy velocity. That's simply volumetric flux divided by area. And instead of diameter of the tube, I'm going to put particle diameter. Whatever it is that I did just now. So I simply took the Fanning friction factor definition and I threw in things that I know about the sphere. So all of these are measurable. Now, if I was modeling bed of spheres, as a collection of these non-intersecting tubes, with constant cross-section, then I would actually use RH as my hydraulic radius. Of those tubes, and interstitial velocity in those tubes, my average velocity, would be related to Darcy velocity as V0 divided by phi. So this is my interstitial velocity, similar to derivation of Karman-Kozeny, and phi is my porosity. And then what I have for one of these tubes, then my friction factor for that tube is Fk over area times kinetic energy density. And if you remember derivation for a tube, it's pressure difference and then area using this hydraulic radius, and divided by my area is area of a cylinder, so it's 2 RHP times L. When I split cylinder open, imaginary cylinder across with imaginary hydraulic radius, right? And then 1/2 rho V square. So when I clean that up a little, there are things I can cancel. Then I get P0 minus PL RH over 1/2 rho V square L.
Why is it the 1/2 2 at the
Let's see, do I have a 4 somewhere?
Is it square the
RH.
term? Maybe.
That is a good question. 1/2 R RH.
Yeah, the 2, the 1/5,
There's still a 2 somewhere. Let's see. So
it's 1. It's not
there's just 1.
Yeah.
Okay. So now, what is going to be the idea here? for tube, I already know my friction factors for different flow regimes. Okay. So what I'm going to do here, I'm going to express this F bed in terms of F tube. So basically I can see that I have this pressure difference that is in both. Okay. So I can actually use that. Okay. And I'm actually gonna then simply see what my F bed is in terms of F2. I'm gonna use my definition of RH because I know that for SpherePack. If you remember, we derived it for Karman-Kozeny. And then I'm gonna, at the end, substitute different flow regimes for tube. Okay? Because I know that from all of the work that has been done on tubes. So I know that like in different flow regimes, I can have different expression. So that's essentially, I'm going to use what I know about tubes, even though it's imaginary tube, okay, and fit it in. And that, of course, will not fit nicely and precisely, so there will be some adjustment of parameters. Okay? But ultimately, if I can get formulas that match my experiments correctly, then I got something, like I got the gist of it, okay? Even if I need to adjust the parameters slightly. Okay, now I'm just still curious. So let's see, where did this 2 go? Let's see if I'm missing it later, okay? Okay, let's save this page. Oops, what is that? Wrong page. Yes?
So that means that friction factor of the sample.
So bed is bed of spheres. Yes, maybe I should have called it FPack, but book calls it F-bed, so I'm sticking with it. Bed of spheres. Or sphere packing.
Then why do we use particle diameter in F-bed? Because in F-bed there is so many particles.
I'm not confused, but that's the only thing I can measure. Okay? Because I want to define in things that are measurable. And particle diameter is something that I measure. So yes, it's a stretch. Okay? By all imagination, it's a stretch. Because I took the tube diameter and somehow just morphed it into particle diameter. Now, it's not terrible, okay? In the sense that if I have a sphere packing, and I indeed look through the, if you're thinking about the sort of inscribed radii of the tubes that are inside a sphere packing, there is a definite correlation with the radius of the spheres. Okay? Now, it's not direct, it's not one-to-one, but give or take my, what we call throats through a sphere packing, if you have a sphere packing of the single size sphere pack, is about 1/5. The radius of the tubes through the sphere packing, the throats, are about 1/5 that of the spheres that are building that packing. But even if it's not like 1/5 or whatever, just like it's a good 1/5 to 1/6 is a good way to think about it. Of course, you can always try to directly measure. So maybe we're missing a factor there, 1/5. But we're going to get to adjustment, so there is no point adjusting it now because later on we'll have to adjust numbers anyway, right? So this is just, so diameter of imaginary tubes through this packing is definitely heavily correlated to the diameter of the spheres. So that justifies putting the diameter of the spheres. with the understanding that we're going to adjust all of the numbers by the end. Again, it's just sort of guiding principles as opposed to strict derivation, because strict derivation is not possible. Okay, so now what we can do is we can basically relate use pressure difference that appears in both to relate F bed and F tube, or rather eliminate pressure difference in both. So I'm gonna express pressure difference from both. And in the first one, it's rho V square L over RH F tube. And it's also, so I can also immediately express rho. So what is my V in terms of V0? This one. Yeah? So that is the first definition, and in the second, this is also equal to, there is 1/2 rho V0 square times 4L over dP F bed. So then dot dot dot, I have a relationship between F bed. This is where I need to double check this 4. My notes have 4, and I'm gonna go with 4 for now. I'll just put a line, double check. And now I just want to also, RH is not something that I know how to measure right now just by RH, but I want to express it. And we had that, recall, Kozenik-Harman derivation. So my RH is phi over specific surface area, and that is comes down to phi times particle diameter over 6 times 1 over 5. And that is cool. I know particle diameter and porosity are 2 things that I do know about the SpherePack. So that gives me my F bed as 3 over 2, 1 minus phi cube, F tube. So this is actually my starting point. 2 pages and I'm still at the starting point. So this is my starting point in the sense that now I'm going to start actually taking this F tube and put different flow regimes in there. One thing about flow regimes is that we need to take a small break and figure out, well, how do I define flow regimes, or what is my Reynolds number for SpherePack? Okay, so Reynolds number for a SpherePack. So in general, I know that Reynolds number for a tube, for instance, would be diameter of the tube, and then some velocity, average velocity, rho divided by mu, right? Now here, instead of diameter, if you remember, diameter originally was thought of as 2 times radius, and then that radius and hydraulic radius are related as radius is 2 times hydraulic radius for a tube, cylindrical tube. So this is why it actually became customary to actually have 4RH rho divided by mu. Now, that said, if I have 2 times or 4 times or even no 4 here in the definition, it doesn't really matter as long as ultimately people agree, well, this is the definition of Reynolds number for a SpherePack, because we know we don't have one strict definition. This is not a geometry that is easy to define. So multiplying by 2 or dividing by 2 is not all that important, okay? Because ultimately, Reynolds number, you go and you measure, and then you know that Reynolds number less than this number means this and this and this, means certain things in a specific geometry. We know already that, for instance, for spheres, what I call laminar flow has to have Reynolds number less than 1 for spheres. Okay? Whereas for tubes, what we call laminar flow has to have Reynolds numbers for tubes less than 2100. Okay? So ultimately, what you define and where you have a certain certain factor 4 or not factor 4 is not all that important. Okay? As long as we just agree this is the definition, and then we go by that definition. So just to actually work it out a little further, so it's actually, if I put RH in there, I should get something like 4 phi dp, average of v, rho, divided by 6 mu 1 minus phi. And this V is often actually, so when what is this? Okay. So you will see, so this is essentially 4 over 6, or 2 over 3, dp V0 rho divided by mu 1 minus v. And I'm gonna remove this like that. So what you're gonna see for SpherePacks typically, so important thing to remember about this is that there has to be porosity somewhere in there. Okay. For a SpherePack, particle diameter, porosity, and Darcy velocity, those are the things that I can measure, okay, from the outside about the SpherePack. I cannot measure average velocity, interstitial velocity through a tube. I can if I have some fancy schmancy simulation, okay, but that's not practical in the lab. So basically, with this definition, I have all of the things in there that I can actually measure about the SpherePack. And typically this 4/6 is actually kind of forgotten. And what you will see in plots often is just dpv0 rho divided by mu times 1 minus v. Okay. But again, important thing is that I defined Reynolds number in terms of measurable quantities about the SpherePack as well. Okay, so now that we have figured out what the Reynolds number should be, then we can actually talk about flow regimes through the SpherePack. So let's now put that together. So we will have to have first a laminar flow. Now for F tube, I know that it should be 16 over Reynolds, right? And I'm going to call this Reynolds H for my SpherePack. And question is, does that fit very well? Well, when compared to experiments, 16 over Reynolds didn't work, but 100 over 3 Reynolds worked better. Fits experimental measurements better. But quite frankly, as long as I get a good fitting to Reynolds number, I'm good with that. So then my F bed becomes, if you remember, there was that functional relationship with porosity related to the F tube, so I'm gonna put that all together. And there is a 75 over, and there is dp rho v0 divided by mu here. Fits experimental measurements better. And this formula is found to work well. Works well for dp rho v0 over mu 1 minus v less than 10. And my phi less than 0.5. So again, this is what ends up being the Reynolds number most of the time for SpherePacks, and that number should be less than 10. Yes?
When did you ever get velocity greater than 0.5?
Precisely. So this is fine. You get in some looser systems, depends what the how good is your sorting. Right. But yes, for all the practical purposes, yeah, that doesn't bother me at all. Hey, I've seen actually some artificial media done with fused particles, and I've dealt with 50-55%. But again, that's because of the particle shapes and the way it is. So rarely, yes.
Just a little confused. So you defined the friction factor of a bed and the friction factor of a tube, and the 16 over Reynolds number like never works, or it just doesn't work in a SpherePack?
Doesn't work in a SpherePack. So I know from tubes, I want to fit in my results from tubes, and then people tried it, and then it's shifted. So they just adjusted the number 16 to 100 over 3.
And that's for tubes within a SpherePack, or
Imaginary tubes, yes.
okay.
Okay, they're imaginary tubes. And I have results for real tubes.
Okay.
So my result 16 over Reynolds is for real tube, but that being Reynolds number for tube, actual tube, not for SpherePack.
Okay.
So here they're like, okay, let's try to fit 16 over Reynolds number for a SpherePack. Okay, just conceptually. And then compare that to experiments. Well, good news is that the match in terms of functional relationship 1 over Reynolds number is pretty good. I just have to adjust the coefficient.
Okay.
But really, what one could have done is say, hey, let's define Reynolds number for SpherePacks, just out of the blue. And then let's just do a bunch of measurements and try to do curve fitting. But if you do that, you're going to have extremely hard times doing the curve fitting. This is trying to gauge the functional relationship with some sort of conceptual models so that you can use that to guide you as a function to fit, ultimately then. And that's precisely what this says. Okay? Because then it actually turns out that it works really well, but I had to come up with my proper definition of the Reynolds number so that what this fitting of the roughly 1 over Reynolds number works. Because look at the complex relationship with porosity. You don't come up with that with guessing, right? So ultimately my friction factor is a complex function of both the Reynolds number for the SpherePack and porosity.
Okay, so
With the understanding that Reynolds number does depend on porosity, right?
Okay, so you need to use both to calculate. Okay.
And that's why I don't want to just like do the experiments and then try fitting, because it's gonna be good luck fitting.
Okay.
Maybe these days with machine learning and stuff, maybe we can figure that out. But this was done, 40, 50 years ago. So without that, you're kind of this whole trying to imagine tubes through the SpherePack and try to kind of upscale that way is trying to look for that functional relationship. And even if I adjust the parameters slightly, I got something right if I actually can do that.
Okay.
Because many times when you have a complex system and you have multiple things that you can measure, it's extremely hard to do curve fitting at the end. So that things kind of collapse properly, right? Yes?
When we solved for the friction factor last week for tubes, we used radius.
Yes, because in tube I have, but we did define it in terms of diameter in the end, radius of tube.
Why didn't we do it in hydraulic radius? Why didn't we do it in hydraulic radius? Didn't we substitute R here?
Because for tubes, hydraulic radius is something that I use for more complex geometries in general. And that's how it came about. If I just have a plain tube, I have a plain tube. What I use doesn't really matter. So why would I use a complex?
Yeah. So why did we assume that R is equal to RH in tubes if we already have it, right?
But R is not RH in tubes. In tubes, RH is R over 2. Okay, because RH is the area, vetted area divided by vetted perimeter. And for tubes, that's R over 2. Now here again, whether you use that 2 or not, ultimately you have to do adjustments like that. So what we're really looking for is the proper functional relationship or dependence. Is it dependence on R or R square, or in this case porosity or porosity square, or so forth, right? And that's basically, so if we use the definition, especially where we actually put in RH for SpherePacks, where I related actual cross sections available to the flow through the vetted perimeters inside a SpherePack, okay? That's that's the key kind of functional relationship to have in there, because it's those surfaces that are basically providing friction to flow, right? And the size of those surfaces will impact the flow the best. So then if I actually get that I can relatively well fit my experiments to these formulas, guiding formulas that I got this way, that I got the gist out of it. Okay, even if I adjust the parameter or two slightly.
So is 100/3 is like curve-fitted result?
It's curve-fitted result.
So 100/3 is like 2 times for 16. So is it there's correlation between like two?
Right, but this was, look, I just substituted Reynolds number for SpherePack instead of the Reynolds number for tube. So that was kind of a stretch right there. Right? So the fact that I have to adjust something, the coefficient twice, is not gonna knock me off my chair. Okay? I already committed one crime, right? Continue committing, right? So, but then I'm gonna adjust it. And it's this part, this functional relationship here, that where you have that, right? This is your Reynolds number. That you can't easily guess if you were gonna curve fit. I mean, that could take some imagination, right? So if you can then curve fit with this, then I'm good. Whatever crimes I committed, they're validated at the end by being able for this flow regime to fit. All right, so that is our laminar flow regime. Then I'm gonna, and it's often actually common to express pressure drop. So it's common to express pressure drop. And that's, I'm just gonna put the final, so if I just express pressure drop through the F bed, I'm gonna get 150 mu V0 over dP square, 1 minus phi square over phi cube. And that is called so-called Blake-Kozeny relationship. Spoiler alert. So what we actually had, if you express the same thing using Kármán-Kozeny, instead of 150, you have 180. That's close enough for order of magnitude is close enough in petroleum engineering, okay? All right, what do we do for turbulent flow? For turbulent flow, if you remember, and you probably don't, as you get like into turbulent flow, the relationship for the friction factor becomes kind of like a constant-ish function. So it's actually, when you compare with the experimental data, you can just throw in a constant 7/12 is a constant that fits experimental data well.
So is that for rare tube or SpherePack tube?
Fixed for SpherePacks. And what I know from tubes is that a constant should work rather well, right? So I'm looking for a constant, and when you look for that constant in SpherePacks, it's 7/12. So my F over bed is 7/8, 1 minus phi over phi cube. And that gives me pressure drop. Pressure drop is what I care about in the lab. As or rather, if it's going up, there's something wrong. And this is so-called Burke, so I'm gonna, this is one relationship that this is so-called Burke-Plummer. Equation. And turbulent, what I call turbulent, is dp rho v0 over mu 1 minus phi larger than 1,000. And what's left now is between 10 and 1,000, right? What we call transition regime. And so this is asymptotic behavior for large Reynolds numbers. I can kind of in my mind equate that with large velocities. And we see velocity squared here. Okay. When I have smaller velocity, okay, then velocity squared will be very small term. So this will be sort of like the guiding relationship. So if I add the two, asymptotically, I'll behave correctly for small velocities versus large velocities. Okay? For small velocities, something like v squared will disappear, and this will be the dominant formula. And for large velocities, v squared will dominate, and this will disappear. So actually, when I add the two, it works surprisingly well. Okay? So that is the transition regime. Is so-called Ergen equation. I can write it next time. It's pretty much the sum of the two. Okay? And it works well in both, and actually it fits the experimental measurements really well too. Okay. All right, see you on Wednesday.